Welcome to the next part on uncertainty propagation. So far I have visualized how it works with one input quantity and two input quantities and how correlations are included. In this video I will show how to extend it to more input quantities. There is less to see this time, as it is hard to visualize more than 3 dimensions. Therefore it will be more mathematical. The main question is, how can systems with multiple input quantities be handled systematically? Therefore, let's first recall the equations for two input quantities. It consists of the partial derivatives of the model function and the uncertainty for each variable. The correlation is included by the mixed term together with the covariance. How can they be expanded to 3 or more quantities? First, I change the notation to write the terms more compact. Then let's get rid of the square root. This will give the squared uncertainty, which is also known as variance. To add a third variable, we need, of course, the sensitivity coefficient and the uncertainty contribution. Further terms are included to consider the correlation between the first variable and the added variable, and between the second variable and the new variable. As you can see, the additional terms will rapidly grow with each added variable. Let's first rearrange the terms. Now I want to recall the equation for the variance and covariance. The variance is just a special case of the more general covariance term. To symbolize that, I will change the notation and write the variance of x as the covariance of x with x. Note also that the terms are commutative. Therefore, the covariance of x and y equals the covariance of y and x. Now let's split the covariance terms into two summands and arrange all the summands neatly into a grid. The variables are now tightly separated along rows and columns. The cool thing now is that this equation can be written as a matrix equation. The first and last vectors contain the same sensitivity coefficients. The last one is a column vector and the first one is the transposed version to result in a row vector. Squeezed between is the quadratic covariance matrix. The diagonal elements contain the variance and the off-diagonal elements contain the covariances. As you can see, the variables are arranged systematically. Note the symmetry of the matrix. Therefore, it is easy to extend the equations to even more variables. The off-diagonal elements describe the correlation between variables. These correlations are often considered minute and neglected in real-world cases. Therefore, the component can be filled with a 0 to treat the variables as uncorrelated. In the extreme case, you can describe the matrix as just a diagonal matrix containing only the variances. The last step is to reapply the square root to get the uncertainty, but that is easy as it is just a number. To summarize, even cases with numerous input quantities can be treated in a systematic and structured way, resulting in a simple matrix equation.